Another place that we encounter rational equations is when we're dealing with proportional quantities. Now, we already know what it means for two quantities to be proportional. Two quantities are proportional if their ratio is constant. That is, we say x is proportional to y if the ratio x over y is equal to some constant. That is, anytime y changes, x also changes to keep the ratio the same. Now, if we take this equation and multiply both sides by y, we get the equation x equals some constant times y. And it turns out that this form is going to be a little bit more convenient to work with. We should understand x is proportional to y as meaning x equals some constant times y. The reason that this is going to be more convenient to work with is that it's more convenient to understand the other terms that describe different kinds of proportionality. Two quantities are inversely proportional if instead of their ratio being constant, their product is constant. We say x is inversely proportional to y if xy is a constant. Again, taking this equation and dividing both sides by y, we get x equals k times 1 over y. And again, we're going to prefer this form because it's going to be more convenient when we start combining things. In particular, we might say x is jointly proportional to y and z to mean x equals some constant times the product of y and z. This is a little bit harder to understand in terms of some quantity being constant. X is equal to some constant times the product of y and z. The last thing that we might include in the language of proportion is we might include powers. X is jointly proportional to u and the square of v, and inversely proportional to z cubed. That means x is equal to some constant times jointly to u and the square of v, and inversely to z cubed. So any quantity that's introduced with jointly proportional, just proportional, or directly proportional, that goes in the numerator. Any quantity that's introduced with inversely proportional, that goes in the denominator. All right, now that we understand this language, let's take a look at the kind of problems that we see these in. It's known from chemistry that the volume of an ideal gas is directly proportional to its temperature in Kelvin and inversely proportional to the pressure it experiences. Suppose some sample of gas has a volume of 5 liters under 2 atmospheres of pressure at 300 Kelvin. What would the volume of the same gas be at 350 Kelvin and 0.875 atmospheres? So, the thing I want you to notice is that this problem has 3 parts. The first part describes the relationship. Volume is directly proportional to temperature and inversely proportional to pressure. The second part gives us a story in which we know everything: the volume, the pressure, and the temperature. I can use that to find K. I plug in my volume, that's equal to K, times my known temperature, 300, over my known pressure, 2. Working this out, I get 5 equals 150 times K. Divide both sides by 150. I get K is 5 150ths, or 1/30th. And now I have an equation that describes this relationship. Namely, V is 1/30 times T over P. I can plug into this with my new situation. T is 350, P is 0.875, to get V is 1/30 times 350 over 0.875, which works out to 13 1/3. At 350 Kelvin and 0.875 atmospheres, the same sample of gas would have a volume of 13 1/3 liters. If you're wondering, I used a calculator to do that arithmetic.